Welcome to another episode of Flux Cyber. In this episode we are continuing with Tryhackme and we're doing the room Introductory Networking. It's an introduction to networking theory and basic networking tools. So we're going to crack straight in with the introduction. So I'll read this and then I'll obviously paraphrase it. I'm not going to try and do it word for word, but the aim of the room is to provide a beginner's introduction to the basic principles of networking. It's a massive topic and this is just a brief overview. However, it will give us some foundational knowledge of which we can build upon for ourselves. The topics that we're going to cover are the OSI model, the TCP/IP model, how these models look in practice, an introduction to basic networking tools. So let's get started by clicking the complete button. Okay, so on to the OSI model. So the OSI model, or the Open Systems Interconnection model, is a standardized model built on 7 layers. I think it's also called the 7-layer model, or the OSI 7-layer model. It's more compact than the TCP/IP model that the real-world networking is based off. However, the OSI model, in many ways, is easier to get an initial understanding from. So the model consists of 7 layers. That's the application, presentation, session, transport, network, data link, and physical. There are many mnemonics floating around to help you learn the layers. This particular person favours anxious, pale Shakespeare, treated nervous drunks patiently. There's a ton of mnemonics around for this, but I'm sure you'll be able to pick your own. So let's briefly look at each in turn. Like I said, I'm going to try and not read all this, but we'll just try and pull bits out and then we'll carry on. So layer 7, which is the application layer. So this application layer of the model essentially provides networking options to programs running on a computer. It works almost exclusively with applications, providing an interface for them to transmit data. When it's given to the application layer, it gets passed to the next layer, which is layer 6, the presentation layer. The presentation layer receives data from the application layer, so the layer above. This tends to be in the format that the application understands, but it's not necessarily in a standardized format that could be understood by the application layer in the receiving computer. The presentation layer translates the data into a standardized format, as well as handling any encryption, compression, or other transformations to the data. So when it's complete, it goes down to the next layer. Layer 5 is a session layer. So when the session layer receives a correctly formatted data from the presentation layer, it looks to see whether it can set up a connection with the other computer across the network. If it can't, it then sends back an error and the process goes no further. But if it can, then it's the job of this layer to maintain it and cooperate with the session layer of the other computer so they can synchronize communications. The session layer is particularly important as the session it creates is unique to the communication in question, which means that you can communicate with different endpoints simultaneously. For example, 2 tabs in a web browser at the same time. So when the session layer has successfully logged in a connection between the host and the computer to the remote computer, it's passed down to the layer 4, the transport layer. So the transport layer is very interesting and that it serves numerous important functions. So its first purpose is to choose the protocol in which the data is to be transmitted. So that's either TCP or UDP. So TCP being the transmission control protocol, which is one that it handshakes. So you have SYNs and ACKs and resets and stuff. And then UDP, which is a user datagram protocol, which is, I think the class is stateless, but it's basically it's transmission is connection based, so it just sends packets of information. It doesn't check whether they've actually arrived. It just chucks packets down the line, so to speak. So this is why video transmission over Skype can be pixelated, because the UDP packet doesn't know that it's arrived. So for situations where accuracy is favoured over speed, UDP would be best, and if you want to make sure that your data actually gets there, so it's TCP. And then that will get transmitted to the next layer, which is the network layer. So the network layer is responsible for locating the destination of your request. For example, the internet is huge. When you want to request information from a web page, it's the network layer that takes the IP address for that page and figures out the best route in which to take. So that would probably be equivalent to your router. So your router would be a layer 3 device. So it works with what's referred to as logical addressing, so IP addressing. Logical addresses are used to provide order to networks, categorizing them to allow us to properly sort them. Currently, the most logical addressing form used is the IPv4 format, which is something like 192.168.1.1, which is what most people's home routers would be, or it might be 192.168.0.1, and your machine could be 192.168.1.10, for example. So that then gets passed to the data link layer. So the data link layer focuses on the physical addressing of the transmission. It receives a packet from the network layer that includes the IP address for the remote computer and then adds the MAC address of the receiving endpoint. So that means that it can send it through the router, and then the router knows where that packet came from. So when it goes all the way back, it can look at the table and say, okay, this is the computer that sent it because we matched the MAC address. That must be the one that it needs to go to. So the data link layer also serves an important function when it receives the data, as it checks the received information to make sure it hasn't been corrupted during transmission, which could well happen when the data is transmitted by the physical layer. So layer 1, the physical layer, is the electrical layer. So that is the one that puts the ones and zeros on the line via electrical pulses, and it's the job of the physical layer to convert the binary data of the transmission into signals and then transmit them, as well as convert the signals when they're coming back. So we've got a series of questions now, which is the which layer. Oh, for the which layer question to answer, but you answer using layer number 1 or 7. So let's get on and do that. So which layer would you choose to send data over TCP or UDP? Answer with the layer number. Okay, so let's have a look. So what would we want? We'd probably want layer 4, because it chooses a protocol in which the data is transmitted. So that's probably layer 4. Okay, so what's the next one? Which layer checks the received information to make sure it hasn't been corrupted? Okay, so if we got layer 2, there you go, to make sure it hasn't been corrupted during transmission, so that's layer 2. In which layer would data be formatted in preparation for transmission? Which layer data would be formatted in preparation for transmission? So when a session receives it correctly formatted data, so layer 5. Oh, whoa, why have I got that wrong? The data would be formatted in preparation for transmission. I wonder if that's 6 then. Maybe it's 6. Have I got that wrong? No. Okay. So what have I got it wrong? What's the question again? In which layer would the data be formatted in preparation for transmission? Is that transmission would be physical layer, right? So maybe it's 2. Is it 2? Which layer transmits and receives data? Well, that's that'd be layer 1. Which layer encrypts, compresses, and otherwise transforms data into initial data to give it a standardized format? I saw encryption further up, so as well as handling encryption, that'll be layer 6 then. Which layer tracks sessions? Which layer tracks communications between host and receiving computers? Well, it's a session layer because it says somewhere in here synchronized communication. So layer 5. Which layer accepts communications requests from applications? Well, that's got to be 6, doesn't it? It's got to be the presentation layer. Oh, accepts requests. Hold on a minute. Which layer accepts communication requests from applications? Well, it's 7. Tell you what, I need to slow down and read these questions. That's one of my learning flaws, is I don't read questions. Which layer handles logical addressing? Well, that'll be layer 3, which is your router. When sending data over TCP, what would you call the bite-sized piece of data? A packet. Yeah, it's the packet, isn't it? When sending data over TCP, what would you call the bite-sized piece of data? I thought there would be packets. Let's read this. Yeah, the packets all get to the right place. Blah, blah, blah. To ensure that data is acceptable speed, blah, blah, blah. Packets of data are essentially thrown. So that's UDP. There we go. Segments. So it's segments. I'm sure that you're all screaming at the screen right now. Which layer would the FTP protocol communicate with? I'd say it would be the application layer. No. Okay. I thought it'd been the application layer because it'd be FTP's the software. Maybe it isn't then. Other transformations to the data. Okay. Is it 6 then? Oh, why did I put 1? Why did I put 1? Is it 7? Have I got it? No, I must have just, yeah, there you go. Again, not paying attention. Which transport layer would be best suited to transmit a live video? Which transport layer? UDP. Okay, so we move on to the encapsulation task. So as the data is passed down each layer of the model, more information containing details specific to the layer in question is added onto the start of the transmission. As an example, the header added by the network layer would include things like the source and destination IP address. So network layer down here. Let's make that bigger. So the network layer, it adds the headers in. Where are we? So blah, 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 blah. And the header it's added to the transport layer would include, amongst other things, information specific to the protocol being used. The data link layer also adds a piece of information at the end of the transmission, which is used to verify that the data has not been corrupted on transmission. I thought that was called a CRC check, cyclic redundancy check or something like that. Could be wrong. So let's just make that big again so we can have a quick look. Application layer, the header's added. Presentation layer, session layer, transport layer, network layer, data link layer, and then the whole encapsulated data is sent as one big packet. So when the message is received by the second computer, it reverses the process, starting at the physical layer, and then passing it up through the layers, and this is called de-encapsulation. As such, you can think of the layers of the OSI model as existing inside every computer with network capabilities. Whilst it's not as actually clear-cut in practice, computers do follow the same process. The process of encapsulation and de-encapsulation is very important, not least because of their practical use, but also because they give a standardized model for sending data. This means all transmissions will be consistently follow the same methodology, allowing the network-enabled device to send a request to any other reachable device and to be sure that it will be understood, regardless of whether they're from the same manufacturer, operating system, or any other factor. Okay. So, how would you refer to data at layer 2? So, layer 2 header would be frames. How would you refer to data at layer 4? Layer 4, it does say if the UDP protocol is selected. So we know that TCP/IP was segments, so it's got to be datagrams. What process would a computer perform on a received message? It was de-encapsulation. Which is the only layer of the OSI model to add a trailer. So that is layer 2, which is a trailer up here. So let's just make that big. So we've got the data link layer, so layer 2 header, layer 2 trailer. What's that asking for? Is that data link then it's asking for? Yeah, okay. Does encapsulation provide an extra layer of security? Well, it did say it did. It did say it was up here somewhere. Maybe it was further up here. There you go. Yeah, it does add a bonus of increased security. So the answer is I. Perfect. So we'll move on to the TCP/IP model. Okay, so the TCP/IP model is in many ways very similar to the OSI model. It's a few years older and serves the basis for real-world networking. The TCP model consists of 4 layers: application, transport, internet, and network interface. Between them, they cover the same range of functions as the 7 layers of the OSI model. So it says, some recent sources split the TCP/IP into 5 layers, breaking the network interface layer into the data link layer and the physical layers, as with the OSI, and that's what we did before. It saw under the encapsulation, it picked it up as data link. This is accepted and well known, however not officially defined. So the 4 layers of an RFC 1122, which I think you can go up and look for these RFCs. You'll be justified in asking why we bother with the OSI model if it's not actually used for anything in the real world. The answer to that question is quite simply that the OSI model, due to being less condensed, tends to be easier for learning the theory of networking. But the two models match up something like this. So application is the first three: application, presentation and session. Transport. Internet is network. Data link. And the physical is a network interface, which kind of makes some sense, I suppose. So, the physical being the plug that you put into your network card, and then the data sort of link, to put the packets on the wire, I suppose. So that does make some kind of sense. The process of encapsulation and de-encapsulation works in exactly the same way with the TCP/IP model as they do with the OSI. At each layer of the TCP/IP model, a header is added during encapsulation and removed during de-encapsulation. So let's get to the practical side of things. A layered model is great as a visual aid. It shows us the general process of how data can be encapsulated and sent across a network. But how does that actually happen? So when we talk about TCP/IP, it's all well and good to think about a table with 4 layers in it, but we're actually talking about a suite of protocols, sets of rules that define how an action is to be carried out. TCP/IP takes its name from the two most important of these: the Transmission Control Protocol, and then which we touched on earlier, and that controls the flow between the two endpoints, and the Internet Protocol, which controls how the packets are addressed and sent. There are many more protocols that make up TCP/IP, and we'll cover those later. So, TCP is a connection-based protocol. So in other words, before you send any data, you must form a stable connection, which is what I said earlier about the three-way handshake. So, SYN, SYNAC, and ACK. So, synchronize and acknowledge, and then acknowledge. And I think there's another one which is reset, RST, I think. When you attempt to make a connection, your computer first sends a special request to the remote server, indicating that it wants to initialize a connection. So let's make that bigger. So that's the SYN. This request contains something called a synchronized bit, which essentially makes first contact in the connection process. The server will then respond with the containing SYN, but as well as an acknowledgement. So it goes from the client to the server, SYNAC bounces back, and then the client acknowledges it and sends it back. So finally, your computer will send the ACK by itself. My word, the best of Frank. Very good. Credit to Kieran Smith at Abertay University. So we're not going to go into exactly how this works on a step-by-step level, not in this room, but it's sufficient to know the three-way handshake must be carried out before a connection using TCP, but not UDP. So it's important to understand why the TCP/IP and OSI models were originally created. To begin with, there was no standardization, and different manufacturers followed their own methodologies. Which is, that's, you get that a lot, don't you? So that's why we have standards these days, like USB standard, and the world's moving towards USB-C as a single, especially here in Europe. They're forcing manufacturers like Apple to go down the USB-C route, because that means everything's more standardized, and Apple didn't want to do that. They had their own Lightning connector, and that's what they wanted to stick with. But they've been forced, and personally, I think it's for the better. But that's just me. So, which model was introduced first, OSI or TCP/IP? So TCP/IP. If I could actually spell TCP/IP, that'd be great. Which layer of the TCP/IP model covers the functionality of the transport layer of the OSI model? So if we scroll back up again, make that bigger. So Transport. I forgot the question now. It's typical of me. Transport. So which layer of the TCP/IP model covers functionality of the session layer? So let's go back up. The application layer. Thinking about it. Still thinking about it. We'll move on while that's thinking about it. The network interface layer of the TCP/IP model covers the functionality of the two layers of the OSI model. These layers are the data link and I don't know why that's an error has occurred. Can we try it again? Yeah, there you go. These layers are the data link and the physical. Which layer of the TCP/IP model handles the functionality of the OSI network layer? Let's scroll up. So where's our network layer? So that's the internet layer of the TCP/IP. What kind of protocol is TCP/IP? I think they call it connection based. I think. Let's have a look. Connection based protocol. What is SYNC short for? Synchronize. Now I don't know whether this is. I'll have spelt this wrong because A, my spelling is terrible, and B, there'll be a difference. There you go. Yeah. Paste that one in. What is the second step of this three-way handshake? So it's you send it a SYN and then a SYNAC. What is a short name for acknowledgement? Well, that's an ACK. Brill, okay, so that's that done. So the TCP/IP model is complete. And again, you know, it's obviously I'm going through these at pace. It'd be better to spend a bit of time and which I will do. I'll go back and reread some of these, but otherwise it'll be a seriously long video. But we'll go back and read these and make sure that they're all correct. So let's get rid of that one, and then we can move on to the next. Task 5, which is ping. At this stage, hopefully all the theories made some sense and you understand the basic models behind the computer networking. For the rest of the room, we're going to take a look at some of the command line networking tools that we can use in practical applications. Yeah, this is what we like. So many of the tools do work on other operating systems, but for the sake of simplicity, I'm going to assume that you're running Linux for the rest of this room. But the first tool that we're going to look at will be the ping command. So the ping command is used when we want to test whether a connection to a remote source is possible. This usually will be on a website on the internet, but it could also be for a computer in your home network if you wanted to check it's configured correctly. Ping works using the ICMP protocol, which is one of the slightly less known protocols of TCP/IP. The ICMP protocol works on the network layer of the OSI model, and thus the layer of the internet layer of the TCP/IP model. The basic syntax is ping and then the target, and we're going to test ping in google.com. So notice that the ping command actually returned the IP address. Can I make that bigger? Notice that the ping command actually returned the IP address for the Google server that's connected to, rather than the URL that was requested. This is a handy secondary application for pings, as it can use to determine the IP address of the server hosting the website. One of the big advantages of ping is that it's pretty much ubiquitous to any network enabled device. All operating systems out of the box and even most embedded devices can use ping. Have a go at the following questions, and any questions about the syntax can be answered using the man page on Linux. I don't have Linux, so it doesn't matter. What command would you use to ping the BBC? So we'd do ping bbc.co.uk. Okay, so ping whatever that is. Let's see whether I can get a ping on here. So I think the question was asking for the IP address. So let's take that. Which switch lets you change the interval of a sent ping request? It's a good question. So I haven't got man pages, but I think on here. So what have we got? So that is a constant ping, T. A resolve. Anything that says interval in here. The only one I know would be T, because that says just carry on, right? Buffer size, time to live, types of service, record the route, time out in milliseconds. The only thing I could think of is T, but I could be wrong. No, it doesn't like that. So, shout at the screen. Could we time out in milliseconds and wait for each reply? Is it tac W then? No. I mean, there's not too many to choose from, right? So T just continues, which I thought it would have been. See, is there more on Linux than there is on Windows? Because I haven't got the man pages. I wonder whether I can do in here ping man page. Okay. Interval is I. Yeah, so I don't have that. So I'm just going to go back because I thought I did see the restriction. Force using, so it'd be TAC 4. Now verbose would usually be TAC V for most things. Whether it is or not, I don't know. Oh, it is. There you go. That's great. So let's close these down. Don't need them. So that's ping. So ping and then the flag. And if you want to check for the man pages, you can do, for the manual, you can do ping, or you'll have to search for it on the internet if you're on Windows, like me. So let's move on. So we're on trace route, or trace route, depending on your local vernacular. So the logical follow-up to the ping is a trace route command. Trace route can be used to map the path your request takes as it heads to the target machine. The internet is made up of many, many different servers and endpoints, all networked up. That means in order to get to your content, you'll first go through a bunch of servers or hops. Traceroute allows you to see each of these, and it allows you to see every intermediate step between your computer and the resource that you requested. So the basic syntax for traceroute on Linux is traceroute and then destination. On Windows, it's trace RT, and it operates using the same ICMP protocol that ping uses. So this is doing a traceroute to google.com, and you can start seeing all the hops and how long it takes. Let's going to make that bigger. Hops and the time it takes for all those hops before you get to your destination. So again, this is going to be a Linux thing, so I'm going to have to see whether I can get the man page for that, because it'll be different for me. So use traceroute on tryhackme.com. So let's do that. Let's go back to where I was before and do trace RT tryhackme. My word, tryhackme.com. Trace complete. Just minimize that. So what switch would you use to specify an interface when using traceroute? I'm going to just guess at TACI for interface. What switch would you use if you wanted to use TCP sync? I don't know, so let's just have a look. TCP SYM for probes, TAC-T. Lateral thinking. Which layer of the TCP/IP model will traceroute run on by default on Windows? Which layer? Is it 5? So 7.6. Is it 5? So session? No, it can't. It's not session. No, it's not transport. I can't remember. Let's go back, because I can't remember. Four. No, see, that's transport. I thought it was transport because it was all to do with TCP/IP. So, which layer? TCP. This isn't the OSI model. This is a TCP/IP model. So if we go back up to that model, in fact, let's go to the OSI model first. So it's yeah, I don't know actually. Is it going to be 7? Sorry, the transport layer, because it's all about TCP/IP. So transport layer. Let's go back to the model. Networking layer. Yeah, it'd be internet. I think it's the internet layer, isn't it? Let's go back to traceroute. Cool. Okay, that's that task done. Oh, we're on to. Let's close that one, and we're on to Whois. So, domain names, the unsung saviours of the internet. Can you imagine how it would feel to remember the IP address of every website you wanted to visit? That's a horrible thought. Fortunately, we've got domains. So we'll talk a bit more how this works in the next task, but for now, it's suffice to know that domain translates into an IP address. So you can remember to type Tryhackme rather than the actual IP address for type Tryhackme. So domains are leased out by companies called domain registrars, and if you want a domain, you go and register it with a registrar, then lease the domain for a certain length of time. So enter whois. Whois essentially allows you to query who a domain name is registered to. So in Europe, personal details are redacted. However, elsewhere you can potentially get a great deal of information from a whois search. For free users using the attack box as a web version of the whois tool. Let's open that in a new tab then. Whois lookups are very easy to perform. Just do a whois and the domain to get a list of information available. So, perform a whois on facebook.com. So let's go back over to our other tab and let's do facebook.com. So all the details are prohibited, but it was registered in 97. Expires in 2034. It was last updated in April of this year. Interesting. Okay, so there's no answer needed for that. What is the registrant postal code for facebook.com? That isn't on there, is it? Because the all this is prohibited. Let's just go back. So what is the registrant postal code for facebook.com? I actually, yeah. Is that because I'm in Europe that I can't see it? I wonder. I don't know. I might have to Google that because I don't know. So let's just Google that because I don't know what the answer is. I forgot what I was doing then. Let's just do that. Anything in here which just comes back? That's facebook.me. What's this? Alright, this is a write-up. They've probably got the answer, right? Let's just have a look. I don't want to do that. Blah, 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 blah. Oh, wait a minute. Why was I... Is that a answer? Oh, that's the answer. No, wait, let's just have a look. Have I just missed something? No, it's definitely not there. No, it's definitely not there. I just thought it was me. Let's bend that off. Let's go back in here. Let's paste that in. Not ideal, but when was the Facebook domain first registered? So I did read that out. 1997, wasn't it? 29th of the 3rd, 1997. 2903. 1997. So now we need to do the same search on whois. So let's try a new one. Okay. So, what's the question? What city is a registrant based in? Redmond. Oh, a bit of OSINT now. What is a golf course that is near the registrant address for Microsoft.com? So if we do that, and say golf course, the golf club at Redmond Ridge. Nope. Golf course. Oh, it's a golf club. Is it the golf club? Is it just the golf club? No, it can't be. Is that like Redmond Golf something then? What is the name of the golf club? I mean, does Redmond fit in here? Redmond. No. Okay, it's probably something stupid that I've missed. I mean, there's that. Is that? I don't think that's it, is it? Let's do that. See, that just says the golf club at Redmond Ridge. So what have we got? We've got Willows Run Golf Complex. No, it's not. It's not Willows Run. Something's. The golf club at Redmond Ridge. Redwood Golf Centre. Is that it? No, because it doesn't fit. Let's look at the let's map. Let's take that out and let's do that. Right, so there's Microsoft. We're scrolling. What have we got? These are on neighbourhood parks. Can I actually put then golf clubs, golf course? Evergreen Golf Club? That's a club, it's asking for a course, isn't it? Golf course. Is it Braeburn Golf Course? I don't think so. Oh. Try and make that come back, eh? Braeburn Golf Course. Nope. We're failing. We're failing, team. B-R-A-E. Have I spelled it right? B-R-A-E. No. See, that just says the golf club at Redmond Ridge. But again, these are clubs, not courses. Cascade Club. Is it Redmond Ridge? No, because Redmond didn't fit. Okay, this is a big fail, team. What about if we take this and actually just try, let's try Google Maps instead. Is that it? Bellevue Golf Course? That wasn't on the other one. Is it that? Ah, Bellevue Golf Course. Got there in the end. That wasn't listed on the because there's Braeburn. That wasn't listed on Bing. So got there in the end. Too long, but there you go. Bellevue Golf Course. It's a bit of a pain, to be fair. So I need to do some more on OSINT. I think my OSINT skills. I'll just not rely on Bing. What is a registered tech email for Microsoft? What have we got? Well, that's not an email. Yeah, I mean it's an email. It's a thing, isn't it? Let's just put that in. What does that give us? Okay, that's great. What is the registered tech email for Microsoft.com? Is it that then? Is it markmonitor.com? Is that what it's asking for? No. What is the registered tech email for Microsoft.com? Is it domains.markmonitor.com? No, because that's not an email address. It's a URL. Okay, so maybe this again it's something that we have to Google. So if we do, let's do who is registered tech email for Microsoft. Don't want to do that. I think that's where we were before, isn't it? That's just going to give us the same results. Try this one. I don't want to do that. I just want to do Microsoft.com. Lots of traffic lights here. This is one of these where it's going to be really irritating. Microsoft.com. Right. So it's all empty. Sweet. Doing well here. Doing well here. I wonder why that doesn't work. It's not something I've seen before. Email contact form not available for this domain, for Mark Monitor. Yeah, it's not something I've seen before. Okay. I don't know what the answer is, so we're going to have to put this in and see whether we can get it. There you go. Okay, so that was a bit of a pain. Sorry about that. I have to really get cracking on my OSINT skills. But like I said, ignore Bing and use Google, I think, is the answer to that. Okay, and we're moving on to task 8, which is dig. So we talked about domains in the previous task. Now let's talk about how they work. Ever wondered how a URL gets converted into an IP address that your computer can understand? The answer is the protocol called DNS, or Domain Name Systems. At the most basic level, DNS allows us to ask a special server to give us the IP address of a website that we're trying to access. So if we want to go to www.google.com, our computer would send a special request to a DNS server, and that would then give it the IP address for what Google is and send it back. And then our machine would know where to go. So let's break this down. You make a request to a website. The first thing your computer does is check its local host file. So basically that's a file that your machine has, and it has lists of domains and addresses that it potentially might know about. So you can put something in your host file. So if you've got like a local network, you could basically map local addresses to domain names if you really wished. It's not really efficient, but you suppose you could do. It's an older system than DNS and much less commonly used in modern environments because we have DNS servers. If no mapping has been manually created, then the computer checks its local DNS cache to see if it already has an IP address stored for the website. If it does, great. If not, then it will go off out to the internet to through your gateway to a DNS or recursive DNS server. So there's lots of these about. Popular ones is Google's 8.8.8 or 8.8.4.4, and then you've got, I think there's 1.1.1.1, I think. So basically, they know how to sort of route that domain and IP address, and then it'll send it back to your machine. So before 2004, there were precisely 13 root DNS servers in the world. These days there are many more. However, they're still accessible using the same 13 IP addresses assigned to the original servers. The balance, so you get closer server when you make a request. The root name servers essentially keep track of the DNS servers in the next level down, choosing an appropriate one to redirect your request to. These lower servers are called top-level domain servers. So top-level domain, or TLDs, are split up into extensions. So for example, if you were searching for tryhackme.com, your request would be redirected to a TLD server that handled .com domains. But if you were searching for bbc.co.uk, your request would be redirected to a TLD server that handles .co.uk domains. As with root name servers, TLD servers keep track of the next level down. Authoritative name servers, that's when a TLD server receives your request for information, the server passes it down to an appropriate authoritative name server. So, name servers are used to store DNS records for domains directly. In other words, every domain in the world will have its DNS records stored on an authoritative name server, somewhere or other. They'll source of all the information. When your request reaches an authoritative name server for the domain you're querying, it will send back the relevant information back to you, allowing your computer to connect to the IP address behind the domain you requested. So, when you visit a website, when you visit a website in your browser, all this happens automatically, but we can also do it with a tool called dig. Like ping and traceroute, dig should be installed automatically on Linux systems. Dig allows you to manually query recursive DNS servers using dig, domain, @ and then the DNS server IP. So, it's a very useful tool for network troubleshooting. So they've done dig, google.com, @ and that's what I said actually before, 1.1.1.1 as a name server. This is a lot of information, and we're currently most interested in the answer section, which is this. Make that bigger. Answer section here, google.com, and then the Google's IP address. Another interesting piece of information is the TTL, or time to live, of the DNS record. As mentioned previously, when your computer queries a domain, it stores it in its local cache, and the TTL of the record tells your computer when to stop considering that record being valid. So basically, if you've got a really low TTL, it will disappear off to the internet DNS server rather than your local cache to get an updated record. That's really good if you're if you do have your own domains and you make frequent changes, then you can set a really low TTL, and then you'll get more frequent changes, but it's not great. So what does DNS stand for? So we've got domain name system. What is the first type of DNS server your computer would query when you search for a domain? It's local, isn't it? Is that local? Will it be localhost? No. First, it's the host file. What's the first type of DNS server your computer would hosts? Is it host file? No. Okay, let's scroll back up. I thought it was host file. The first thing your computer does is check its local hosts file. Have I spelt it wrong? No. First type of DNS server. Is it recursive? Is that the answer it wants? Recursive? Okay, it's recursive, okay. What type of DNS server contains records specific to a domain extension? Use a long version of the name. It was the authoritative server, wasn't it? Authoritative name servers. Sorry, I'm just reading I'm in this top level. Oh, is it a TLD? Actually, it's top level domain. Actually, thinking about it. Where's the very first place your computer would look to find? That's a hosts file. Google runs 2 public DNS servers. One of them can be queried. I said that before. It's 8.8.4.4. If a DNS query has a TTL of 24 hours, what number would the dig query show? It's a good question because I don't know. It's measured in seconds. So I don't know how many seconds are in 24 hours. So how many seconds are in 24 hours? There you go, there's the answer. Bro, okay, so that was dig. So now we're on to some further reading. Okay, so that's us completed our whirlwind tour of networking. Hopefully you found it informative. Networking is one of those things that you just need to learn. We've covered it very basics, but it's a good idea to continue to learn by yourself. In terms of other further information, you can reach out to the Tryhackme Discord. There's also the Cisco Self-Study Guide. And all of those, will be in the room, these links in the room. So there's no final thought needed. So let's just... And there we have it. That's the room completed. So let's just have a quick recap. We went through the OSI model. We mentioned encapsulation, the TCP/IP model, And then we looked at the tools ping, traceroute, whois, and dig. And we had a bit of a battle with some OSINT, where we realised that, really we should be using Google because Bing wasn't that clever. So I'm going to leave it at that. I hope you've enjoyed the video. And again, this is just me continuing to learn. And hopefully you'll stay with me and follow along and we can learn together. If you've got any comments, please leave them. Let me know. And obviously, if you're not subscribed, feel free to subscribe. And that lets me know that, to make more videos. But have a fantastic day.